Right. So my name is Sam Procter. I'm a senior architecture researcher and the initiative lead of the model-based engineering team here at the SEI. So the problems that we work on are ones that can be solved by building models of systems and then analyzing those systems. Today I'm going to be talking about an ongoing research project that we're looking at how safety and security engineering can work together. So the problem space that we're working in is what are called critical systems. These are systems whose failure is intolerable, either because it will cause the failure of the mission or a loss of an unacceptable amount of money, or even injury or death to a human. And so you can see some examples of those up on the screen, but too often, even though these are both safety and security critical, those teams work in isolation. What's more, even setting those problems aside, the pace and the scale of modern system development is such that traditional development techniques can no longer keep up. So what we do in model-based engineering is look at how the architecture can support developer intuition and also, in this case, be used to improve safety and security. So I'm going to be talking a lot about AADL, which is the architecture analysis and design language. You may also be familiar with SysML, which is a similar language in this area, or other model-based engineering languages and techniques. I want to stress that these are for more than research. And in fact, the second half of this talk is going to be given by my colleague, Alex Boydston, so you can hear how previous SEI research is now being used by DoD practitioners. So let's talk a little bit more about AADL. The fact is you can represent a system and its requirements and what it does in myriad ways, from very informal, I could just tell you about it, to mathematically precise, unambiguous statements. And AADL is just such a formal language for this research. It's a published international standard, and SEI is the leader in this area. And so what you're going to see is that with this precision that you get from AADL, there are a number of benefits. So I'm going to introduce AADL by talking about a modern smart building, or a part of one, much like the building that we're in now. So these are buildings that use computers to keep everybody more comfortable and also save energy. So I'm going to talk about this the way engineers are talking about problems all over campus and indeed around the world with a box and line diagram. So you have a box up on the screen, and this represents a computer process. The difference between something that I could just draw on a whiteboard and this particular box is that AADL has, like I mentioned, precise semantics. These are, instead of just English, we're using a computer language that is backed by sophisticated mathematical formalisms to represent, in this case, a protected region of memory and a space where we can allocate individual threads. And so we can analyze that and we can actually generate code off of that. So then we're going to put some threads in our process. Again, these threads are just boxes. But once again, these boxes have these very precise meanings. And I want to stress that you don't need a PhD. You don't need to be a researcher in this area to use this language. That's all handled under the hood. And so we have our boxes, and I promised some lines. And so we have some intra-process communication going on between these threads. So these threads can be connected together by these different sorts of arrows. And you can see that the arrowheads are a little bit different, and that's important because that signifies that there are different types of inter-process communication. So we can attach additional semantics, in this case, the timing and trigger behavior. There are extensible property mechanisms in AADL, so you can have additional arbitrary properties to guide system analysis and code generation. So in this little example here, we have a sensor on the left, which is just a thermometer. It's going to wake up every few seconds. It's going to say, is the temperature comfortable? And if it's not, it's going to kick on a fan. That fan is not going to wake up every few seconds. Rather, it's only going to wake up when a particular message tells it to turn on or turn off. So these sorts of systems are used not only in this building, but you can imagine the complexity if you're building something like a helicopter, that there are going to be little systems like this that are used as components in larger systems, and getting all of that correct is critical to having the safe and secure and dependable performance that we expect from these systems. So that's the world's quickest overview of AADL, and I want you to keep in mind that really what this talk is about is how we can transition research to practice very effectively using languages like AADL. In fact, if there's one takeaway that you take from this talk, it is that really this work is about transitioning research to practice. And that's because AADL is foundational to both new academic research being done here at the SEI and at universities around the world. It is also being used right now by practitioners in the DoD. And so there's this really cool pipeline that we have built where professors are using the same things that practitioners are. And so that cool idea that that professor or that grad student has can get in the hands of a practitioner with really incredible speed. So this particular project consists of a handful of tasks that are at various stages on that pipeline that I just told you about. All of them are implemented using AADL, a language that, like I said, is already in use. So let's talk just a little bit about some of these tasks to support various roles like the system auditor, tester, and designer that you see on the screen. So the first one is a reimagining of what hazard analysis can be. This is one of the more research-oriented tasks. And what's cool about this is that hazard analysis is a way of assessing a critical system safety. So when you're building one of these helicopters or a medical device, you want to think, will it be safe? Will it do what we think it will do and nothing else? And the traditional way of assessing this is with things like fault tree analysis or failure modes and effects analysis. What though if, since we have this computer-backed, very formal representation of the system, what if we could allow an auditor to query the system interactively instead of just getting a stack of paper or a big 500-page PDF that describes the system safety? What if they could say, what would happen if this component doesn't behave correctly? Or what would happen if this component fails in a particular way? Maybe our thermometer sends the wrong temperature. Maybe another component can compensate for that, or maybe it can't. But since we have a model of the whole system, we can trace that failure, we can trace that information all the way through the system. So this analysis is in some ways a visualization built on top of state-of-the-art work being done by Kansas State University. And in fact, Kansas State is one of our collaborators on this project, and I want to talk about a second task that they're actually taking the lead on. So this is a little bit of a complicated diagram to go through as quickly as I have to go through today. So come see me at the poster if you think this stuff is as exciting as I do. But the short version here is that we have our temperature control process up on top. And you can click a button, and from that AADL, you can generate what's called Slang. And Slang is a safety critical subset of Scala. If you're a developer, that's probably very exciting. If you're not, let me just say that it is a very rich language that has a lot of capability to concisely express behavior in ways that traditional safety critical languages may not. So right now, if you're writing code and you have to verify it, a lot of times that language is going to be sort of clunky and your developers are not going to like using it very much. Slang aims to solve that by being a modern language, but still being safety critical. So you can write your behavior in that language. And remember, a lot of this is generated from that AADL. You can verify the crud out of it. You can make sure that it does exactly what you want and nothing else. And then you can click another button to use the HAMR tool to generate the C and C++ that will actually run on your platform. Again, if you've worked in this area, you know that we're not going to be running this code on a laptop like this one. We're going to be running it on specialized embedded boards. And one of the cool things about HAMR is that it's modular, so you can target this to the specific board that, that your system is going to be using. So in addition to tooling and implementation tasks, I also want to tell you about one more, which is just some guidance for designers. So we have some work going on with safety and security design patterns. And this is a great example of academic research where these patterns were published some by the SEI and some by academics around the world, saying here is the right way to do common safety and security design tasks. So here you see some AADL that implements the triple modular redundancy pattern. This is really important if you want to avoid a case where your system has a single point of failure. But it's really easy to accidentally wire things incorrectly or to build your system in such a way that even though you have 3 of something, one of them can fail and take down your whole system because your wires get crossed or because you weren't sufficiently careful or even capable in some cases of building these very sophisticated design patterns. But what we can do with AADL is check these automatically. We can say, this designer has claimed that they're implementing triple modular redundancy. We click a button and we verify whether or not they actually implemented it correctly or not. So now you're familiar with some of the research, but I want to hand things over to my colleague Alex Boydston, who's going to tell you about how AADL is being used by practitioners in the DoD and listen closely for a number of previous research projects that have been done by this group and how they're being used by those practitioners.
Hello, I am Alex Boydston, and I'm a project engineer working on an S&T project program called Joint Multi-Role Mission Systems Architecture Demonstration that's preparing the Army for future vertical lift. And I also have another hat. I'm a project engineer with the FARA program, or the Future Attack Reconnaissance Aircraft. And we have been applying this AADL technology with architecture-centric virtual integration through our S&T projects, and we have a transition plan and a plan to apply this to our future vertical lift program. So JMR, we've been conducting JMR Mission Systems Architecture Demonstration since about the 2012-2013 timeframe. We've had an increasing complex demonstrations that we've been carrying through and applying different techniques for our modular open systems approach to developing our systems. We know that in the past we've had some challenges, and I will talk to you about some of those with the COMANCHE program, which had similar issues that the Joint Strike Fighter and other programs in DoD have had. It's very difficult to integrate software and hardware and get that right and come to the actual integration time and not have issues. We want to mitigate that. So the whole philosophy behind ACVIP, or architecture-centric virtual integration process, leveraging AADL, is to identify these issues early and make them so that we don't have that cost impact when we actually get to the integration of our systems. But here you see there's multiple facets with joint multi-row. It's not just about doing ACVIP or AADL. We've developed a joint JMR comprehensive architecture strategy that goes through a reference architecture, an objective architecture, and a system architecture, those different levels. I could give you a brief on that for about an hour. I don't have enough time. You can talk to me about that later. Then we've also been applying this reference framework called JCA, or Joint Common Architecture, and then we have other, trying to leverage the use of FACE that you may be familiar with, Future Airborne Capability Environment, and HOST, Hardware Open Systems Technologies. We've been trying to apply these multiple open systems standards and technologies, but the analytical aspect of that is to be able to capture the architecture. And when I say the architecture, I'm talking about the system, the embedded system architecture in an AADL model, and analyze that model to identify problems, things that, as Sam was just talking about, with safety and security in our efforts. So we're trying to get to a better means of doing acquisition. We've been doing model-based acquisition in our S&T programs, try to improve integration. We need rapid fielding. We need agile processes applied to our systems in the future to get the capability to the soldier where they can fight the fight. And doing that in an area where you've got to certify and qualify and make it so that it's airworthy is rather challenging. But we've got to do a better job of that in the future. And we want these improved capabilities. We want to be able to port and reuse software. We want to be able to integrate these necessary capabilities in our systems, but that comes with a cost. And qualification, as I said, is very challenging, whether you're doing it for the safety aspect or the security aspect, just to get an airworthiness release. COMANCHE was definitely a challenge. We started out with the intent of buying over 5,000 of these vehicles. Well, as time went on, things got very, very tough. We had difficulty with integration on that system, and the cost increased dramatically, starting out at $12.1 million a copy, and then that escalated to $58.9 million a copy. Why did that occur? Because all of these features that we were trying to add, features that would be implemented in software, and the integration of that software into the hardware, and trying to understand the timing aspects, the safety aspects, the security aspects, it really was challenging. So, in fact, the cost here got so high, it was towards utilizing 40% of the Army's budget, and so therefore it was cut. The first increment of software that went into that aircraft 75% of that had to be reworked. And then the second increment, about 50% of that software had to be reworked. What's the problem there? We didn't really understand how to do that integration, so we need to improve that. So what's the solution for that? We've been utilizing model-based systems engineering on our S&T programs, utilizing SysML, which is all good because, as Sam had alluded to, it captures the big system requirements. There's a need for that. In the Navy's systems engineering transformation, working very hard to do that in PEO Aviation's efforts for model-based systems engineering to meet the DoD's strategic digital engineering strategy, we're looking at that. But there's an element that's more focused on the embedded computing system, that area that's been challenged, the software integration in the hardware. We've got to address that, and architecture-centric virtual integration process does that. We've actually been applying AADL, the tools. We've got a methodology. We have a set of handbooks, ACVIP handbooks, one for acquisition management, one for modeling and analysis and an overview. And we've contained that, and actually we're tracking that. We've got that under configuration management. We have a version of that we are applying on our JMR capstone program, our last S&T demonstration, so that we can convey that again and transition to that to the future vertical lift program of record. What is ACVIP? It originated out of, there was a commercial consortium called the Aerospace Vehicle Systems Institute, led the system architecture virtual integration, and they were looking holistically at the development of systems of realizing that, hey, the cost of software and software integration is getting so large, we're going to have to do something about this. We are having difficulties in integrating the Boeing 777 and the 787, the Airbus 380, and then we in the military, of course, have faced those challenges with F-16, F-22, F-35, and with COMANCHE, as I mentioned. So something had to be done about that. Savvy was looking holistically at the aircraft. There was a lot of different elements of that. They created something called the model bus, which is analogous to the authoritative source of truth in the digital engineering strategy, where you're communicating all these different kinds of digital models and analyses and capabilities. Since we knew that our big area that we're weak in is the integration of software and the hardware, with ACVIP, we really have been focusing on that integration aspect. So in 2013, we coined the phrase of architecture-centric virtual integration process, which was a spin-off of Savvy effort. And it's really focusing on the embedded computing systems, looking at the integration of the system with regards to safety, security, resource analysis, and just assurance of the system to make sure that those things work. And we also have an element of continuous virtual integration tests, which lends itself to an agile process so that we can continually investigate through the model the integration of the system. So what you do is you start by modeling at a high level, and you get more specific, and then you can conduct these analysis on the model as you go. And so the whole thing is we're going to have a better assured system with less integration issues, maybe not totally removing those integration issues, but doing a greater impact to reducing those issues when we get to the release of the system. And we believe that in order to have a truly open, modular, open systems approach, that your system has to be analyzable at the interface level. And we're taking software components with face, or even software components that are not face conformant, and asking that our vendors provide these interface equivalent of an ICD, where you've got the interface structurally and also behaviorally to be able to understand how the interaction of those components would be, and then being able to bind the software to the hardware. You can do that with AADL because AADL, as Sam had mentioned, has very strong semantics. Its semantics, the representation in AADL lends itself to representing an embedded computing system. It has bus, memory, processes, threads, those types of things which you're concerned about for an embedded computing system. It allows for compositional analysis. On the HACMS program that DARPA ran, they ran through formal analysis using the Agree and Resolute capabilities by Collins that's leveraging AADL. and they were made for a more secure system, and I'll talk about that some more here in a moment. So virtual integration, software, hardware systems supporting verification, airworthiness, and safety. And so our first demonstration, I won't go through every one of our demonstrations, but our first demonstration was JCA demo. The SCI and AvMC conducted a safety analysis, requirements analysis. Requirements analysis was using the ALISA, the architecture-led integrated system assurance approach that was listed on one of Sam's slides a while ago. And basically, Peter Fowler conducted analysis of this integration. We went out to acquire a face UOP called the Data Correlation Fusion Manager from two different organizations. One was the Bowen-Sikorsky team, and one was from a Honeywell team, and the government did the integration into a system that we didn't tell them about, but we knew what the system was. It was a modular integrated survivability system on two different operating environments. They did not know what it would be. That was to prove out face, but we had SEI and AvMC to actually conduct a shadow where they conducted the requirements, safety, and timing analysis on the system. And you can see here there are results that are produced. These reports are available on SEI's site and AvMC's site, and also in DTEC if you want to look at them. But over 85 issues were found, and a lot of these issues were found before we even did the kickoffs. And surprisingly enough, we go into the kickoff meetings, and the component suppliers were asking these questions that identified, that agreed with these issues. And then later, we had the government integrator to validate several of those issues. So we believe that ACVIP and the application of AADL was well worthwhile, and we continue to do that on our next demonstration, which was and also here's popped up some of the work that the SEI had been funded to actually support some of this. But later on, we conducted this on the AIPD, which was Architecture Implementation Process Demonstrations, and proved out that this was worthy to go forward. And we continued to mature and get the processes, which is signified in the handbooks and also the tools, get those improved for our last demonstration, which is capstone. So I think this is my last chart here, which indicates several different things beyond just JMR. JMR is listed there at the bottom. But in the 2008-2009 timeframe, Dr. Peter Fowler conducted an analysis on the health and usage monitoring system for the Chinook. And he identified 20 issues that headed off a 12-month delay to this 24-month program. That's a large amount of money there. So that's very significant. And this was before we even coined the architecture-centric virtual integration process. And he did that with AADL. On the U860V, I thought this was very significant because AED said, hey, you Northrop Grumman, shall do some analysis against the UH-60V. And they did, but the problem was we didn't have it in the deliverable. So they identified that there was going to be an issue with using multi-core processor by turning off all these processors. Well, lo and behold, what are we having to face right now? There's a problem with running a single core processor. Had they listened to that, well, then they could have headed off a problem, but that got missed. And then DARPA, as I mentioned earlier, they had this high assurance cyber military system effort where they applied the AADL with formal methods analysis on unmanned systems, be it unmanned quadcopter, a TARDEC unmanned vehicle, and then the Little Bird. The Boeing folks said, hey, you cannot break into our system. Before they applied these formal methods analysis, it took them about 45 minutes to break in, overtake that helicopter, and by doing a red teaming attack on it. And then after they did the formal methods analysis, they were unable to crack in it for the duration of the HACMS program. That program is being carried on with CASE, with cyber assured systems engineering that DARPA is working. And then I've talked to you about JMR, which our very last demonstration, AIPD, said that showed to us, indicated that yes, you do have a 3 times increase in cost to actually to do the modeling and analysis, but on the tail end, you've got a 10 times savings, and that was what one of the reports that came out of that. So that is pretty significant, and I believe that it shows that there is a benefit in doing that. And here you can see some of the efforts, the funding that has been sent to the SEI to help with that. So one thing I want to say before I release, and then I'll take questions, is next week we're doing an AADL User Day in Arlington, and on the November the 18th through the 21st is AADL training. So if any of you are interested in that, you can ask me further about that. Any questions? Okay, what metrics do you use to determine the additional assurance is good enough? Many of us use reliability, 0.999, et cetera, survivability. Well, we have been looking at metrics on our S&T program. In fact, for Capstone, we have several different metrics that we're tracking with, and I didn't get into the explanation of all the Capstone activities, but we have 3 mission system integrators and a JCA product developer that's developing software. So we're tracking their time of effort with doing the virtual integration analysis. We are still tracking lines of code, ESLOC with that, and tracking, the number of issues that they identify by utilizing the virtual integration process versus, and then trying to make projections out of that. Those types of things are being tracked. There's a litany of those things that are being tracked by each MSI. So hopefully we'll get some report out. And then you say, is AADL open license? Well, you can get the AADL standards under SAE. It's an open standard. So you can go to, it's AS 5506. The OSATE, the open source AADL tool environment, can be downloaded from osate.org. And there's very low entry cost tools that Adventium has. If you Google MBE and Adventium Labs, you'll go to their CAME site, C-A-M-E-T site, and you can see more about that. It's $2,500 for 5 licenses. And then there are other cyber companies out there that offer tools. We've been dealing with Physical Optics Corporation. They have a co-simulation tool, and also IDT, the SEI has been working with them for a model-based testing tool that they have that's leveraging AADL. And there's other tools that are coming aboard. ANSYS has got work with their SCADA architect, and also Dassault is working on having some implementations for AADL to support it. So it does exist, and no, it's not SysML, but we're working with trying to bridge that gap too. So I can talk to you further about that if you got questions.